Hello, this is Dr. Hassan Abdullah with the course Deep Reinforcement Learning Fundamentals. And the topic which we are covering is introduction. And the subtopic is 1C. So we are at a slightly difficult level of the introduction. And in this topic, we will be covering some applications of deep learning and reinforcement learning also. Now, as before, this lecture uses the personalized learning management system, easymcq.com/goget. This is the learning management system and it has many wonderful features. And you can access this learning management system by using the URL in the green. And you can view the videos about this learning management system for the maximum utility by following the URL given in the blue. Now, there are 6 videos which explain the features of this learning management system. And those features have been developed by input from students like you, users like you. So it allows very powerful full text search, advanced and basic search throughout the content of this course and other courses which are available here. And any students which have any visual disability, they can change the interface as per the font, the size, the color, the line spacing, and so on. And the text and the contents are optimized. They have diagrams, they have a hierarchy, and you can track your progress so that you know which subject you covered, which topic within that subject, and which question and answers which you covered. And of course, you can assess your performance, your learning, your knowledge accumulation by using the online testing system, which provides the details and your highlights, your weaknesses also. So the approach in this course and in other courses available at easymcq.com is a combination of the Q&A approach and the traditional slides based approach. So the slides based approach is not interactive and it is not thought provoking, it is not very engaging. So those features are included, and the traditional approach has details which are included in this approach. So basically what we do is a blending or a blended learning approach for your benefit. So, what topics are covered in this course? This is the list of topics, and we are at the first topic, which is introduction. So, which consists of 15 questions and answers. Now, these questions and answers are basically concepts. But since we are following a Q&A based approach, therefore, these questions and answers are basically the topics. So, we are at the third and the last subtopic, which is 1C, and some popular applications where we look, and you can see in the blue highlighted region of the Q&A, which are the concepts, that what would be covered in this video lecture. Now we move on to the details of this video lecture. So we are at lecture 11C of deep and reinforcement learning, and we are looking at some popular topics and applications of deep learning. And there is a whole topic which is use cases of deep learning and reinforcement learning, which we will cover towards the end of this course. So, just to give you a brief overview of some of the popular applications of deep learning. So, image recognition is one of them, and it excels at image recognition. Uh, Excels means that it can do a lot in less time as compared to humans. And then is the natural language processing. We have seen it high quality text being generated and text being understood, and autonomous driving also. So we have autonomous vehicles from different companies. So let's cover them, and I'll show you and explain using a diagram also. So let's talk about image recognition. Of course, the details are given here. Okay, all the details are here. And there is the diagram which I was referring to. So let me enhance this diagram and magnify it. So image recognition, right? So this basically is done through convolutional neural networks, and there's a whole topic of convolution neural networks. And the strength is the power of image recognition by automatically learning the features. And those features are not the way we look at them, okay? Because we look very differently. The way we recognize or differentiate a cat from a dog. So that those features are for deep learning. They are like edges and textures, and the objects which are formed through raw pixels, and we humans, we don't have that kind of image capacity to look at the pixels, and if we look at the pixels we lose track of many things. So these techniques outperform traditional methods, right? Okay. And for facial recognition, for medical imaging, for object detection, okay, and basically it eliminates the human in the loop. And what was the human doing was manual feature engineering. So what we can see here, let me so what we can see here that this is the raw image, okay, these are the raw images, okay, and we do a pre-processing, so the images are resized and they are cleaned also, and they are normalized, and then they are split into the training set and the validation set, right? And of course these images can be include cats also, or maybe we are looking for a certain breed of a dog, okay, and then the training and the validation takes place, and you see that there is no human in the loop, right? And then is the, of course there is the inference and the deployment. And the inference is that you are given a new unseen images, and of course they are categorized or classified, and the system and application is deployed. So that's what I was talking about. All right. So we will discuss this and more towards the end of this course, because we have. All right, so let's now go to the, okay, here. So image recognition, then is the natural language processing. So there's a whole course of natural language processing which I teach, and that course is available on this website along with the videos. So what happens is that deep learning has, as a matter of fact, revolutionized natural language processing. Okay, by using RNN and RNN, which we will be covering in this course. Okay, and the uh, transformers like BERT and GPT. Basically, what the transformer does is it captures the grammar of the language, and then we train the model for a specific domain, and that grammar is used along with that domain. So that's not part of this course. And the transformers for capture the grammar, the context, and the semantics. Semantic is the meaning, and where they get it, they get it from the large text corpora. Corpora means, which is covered in the course, large collection of text used for training. And these models, okay, these deep learning models, they outperform the traditional approaches which were used in machine translation, or the text summarization or sentiment analysis. These are the applications and chatbots, and of course that offers a nuanced understanding of the language, right? And it has and the capacity to process long range dependencies effectively. Long range means that we are talking about something, and something is referred to after say 5 words or 10 words, and so there's a long range. So that's another application of deep learning. And then is the autonomous driving. So there are many companies which are offering which have autonomous vehicles, and deep learning enables those vehicles, right, help them. And of course those autonomous vehicles, this is also the domain of reinforcement learning also, but over here we are talking with reference to deep learning. So these autonomous vehicles are able to perceive, and they are able to interpret the environment, and how it does it using cameras and using sensors. And there are neural networks also involved, which handle the tasks such as detecting the lane, or recognizing the object, such that some object on the road, that object could be a car also, or part of a tire also, and then making the corresponding decisions. So these systems are not rule based systems, okay. These are not, I don't have a diagram for this. These are not but I have do have a so these are not like rule based systems which have limited application and capability. So these deep learning allows continuous learning, okay? And of course, with the process of learning is the process of adaptation. So that helps in making real time decisions. And of course, that helps in safe navigation and under complex driving conditions also. So these are the advantages, okay? Now you can think of the Curiosity rover on the Mars. So it takes couple of minutes. I don't know the exact number, but for a signal to move between Earth and Mars. So cannot like send signals or directions to the Curiosity rover. And how many rules are gonna put into Curiosity rover because we don't have that kind of gravity and the terrain here. So that's a good example of autonomous driving. All right, so let's move ahead. All right. So, what are some popular applications of reinforcement learning? Good. So, reinforcement learning, game playing. Now, remember one thing: reinforcement learning. You don't tell the machine the rules of the game because those rules can be a very large number. So you play with the machine, okay, and the machine, of course, gonna make mistakes because the machine didn't knew the game, and by virtue of those mistakes and by virtue of the mistakes not made, the machine learns, okay. And that is about several decades when the IBM machine, as a matter of fact, defeated the chess champion, right? I would not like to tell the name of the person. So reinforcement learning excels in game playing, okay, and it enables the agents, right, to learn the optimal strategies by how? By through trial and error. So by trial and error, okay. And of course there are models, right, the AlphaGo and AlphaZero, which have actually achieved superhuman performance, not by any rules but by self play. And how they do that? They adapt to the opponents, their moves, and they master the complex rules without explicit supervision, right? You play, and then you learn that machine. So they actually end up outperforming traditional algorithms in strategic planning and long-term maximization of rewards. Because this is not searching. Remember, this is not searching because searching is very memory intensive, right? It requires a lot of space. So this is not searching. This is trial and error. Reinforcement learning is trial and error. You make a move and that move results into a penalty, so to say, and then that move is not made, and so it could be a greedy approach also. Anyway, all right. So then is the robotics control. Okay, what is robotics control? Game playing. Let me show you a picture that I have over here, and that picture basically is more yeah, this picture basically, this is reinforcement learning. So we have the states and we have the reward, which we discussed before, and we have the environment. So this is the chess, and of course you make a move, you take an action. If you take an action, you move this piece, right? I don't know chess. My apologies. So I cannot explain the benefits of this move. And then basically corresponding to that move, there is a corresponding state, and corresponding to that move, there is a certain reward also. So we have the reward and the state. So we have this initial stage, and then the agent makes a move, takes an action, right? In the environment. Environment is the chessboard, and then we have the next state, and we have the reward also. And of course this move may result in this piece being like killed, or whatever is the right terminology for chess, or it may move ahead, and of course this is the way it learns. So this is reinforcement learning, right? So we have discussed this diagram before. So what I am talking about, that is explained here. So game playing we have discussed. So robotics control. Now reinforcement learning enables the robots to learn the control policies. And how do they learn it? They interact with the environment, right? And when they interact with the environment, they receive feedback. So it's a process. This is a continuous process of actions. And of course, there is uncertainty, but it is better than the traditional models, right? So it is very nice for like a movement, like which in technical term is called as locomotion. or grasping, or like picking things or picking objects, and navigation, moving among the obstacles. So reinforcement learning, what it does, it allows the robots to adapt to the changes in the environment. Maybe there's a things are moving, right? And learn from experience. So that experience could be a good experience, which result in a reward. It could be a bad experience, which result in a penalty. And this improves over time. And the key thing over here is that it does not involve manual programming. That is the key. There is no manual programming. Okay, and then we have my apologies. And then we have the dynamic optimization. So, what is dynamic optimization? Like traffic management, like resource allocation. The items are continuously being sold and the items are being brought, and or this is like resources which are given to a CPU, or financial trading, which is called as algorithmic trading also. So the bottom line is that reinforcement learning outperforms the static models, okay, which have been used for quite a while, right? And and how it is done by learning the strategies which are adaptive, and this is based upon real-time feedback. So it is, but try to understand that it is not that you put a RL system, a reinforcement learning system for algorithmic trading. That system has to learn, unless of course you put a system which has already been trained. Of course, that has a lot of value. So these reinforcement learning systems, they excel in the environments where conditions are changing frequently, unlike the old systems. And that allows the agents, which is the entity, okay, to balance exploration versus exploitation. That we will discuss when we go to the topic of reinforcement learning, the difference between exploration and exploitation, and over the period of time, that results in optimized decisions. Okay, and remember one thing, that it can handle delays also, and non-determinism, okay, also, and the outcomes are effective. So this is, which is, of course, that requires a lot of processing power also, that requires a lot of data also, which we have already discussed, not discussed, but which we already covered, and we will cover more of it. All right. So let's move on to the next Q&A, or the topic. So how can, this is very interesting, how can face recognition algorithms surpass humans matching faces over changes in illumination? This is a very interesting question, or the concept. So, what empirically, or by experimentation, or by using data, what has been determined is that these systems, reinforcement learning systems, okay, the quality of the results, okay, of identifying humans faces over, that they perform better under changing illumination conditions. So how it's possible? So let me show you a picture here. I see a set of pictures. This is all the description. So you can see that this is the same person, right? The same person, and you can see that the illumination, the angle, the position, the amount of illumination has changed. And if you look at these pictures, I as a human, this person does not looks, okay, exactly as this person, okay, and same is true for this person. But using reinforcement learning, the quality of recognition is better of the agents as compared to humans. So how it happens, okay, how is this possible? So that's a use case. So basically, what they do is that in these changing illuminating environments, those features are used which are unaffected by the light, the amount of illumination and the angle of, or the source of the light. Now the problem with us humans is that we are sensitive to, which is called as the visual noise, right? So that kind of hinders our recognition. And but that is not the case for the machines. Okay. So what the algorithms which are used in reinforcement learning, they use consistent patterns, okay, which are not affected by illumination, and the training is across different diverse conditions. So what is the outcome? The outcome is that the results are more accurate, and not only they are accurate, but they are repeatable. Okay, where in the low light environments, where there are shadows, where there are high contrast environments. So that is the domain where reinforcement learning surpasses humans. Okay, and then what is other factor is the other factor is robust feature extraction. So what is that? Basically, these algorithms, the reinforcement learning algorithms, they extract features like edge maps, the same thing which was done in deep learning also. They extract contours, they extract landmarks, right? And so those which humans cannot perceive or understand. And what is special about those features, that they remain relatively unaffected by the light changes, by the angle of the light, and which is not like human perception, because we as humans, we struggle with the shadows, with the glare, and with the contrast. So this is the robustness of the reinforcement learning system and their algorithms, which result in higher accuracy of recognizing images under challenging illumination conditions. Okay. All right. So the next point is illumination invariant features. What it does means, for example, like local binary patterns or deep learned embeddings. Okay. So that help the algorithms ignore the variations in lighting. Okay. So instead of focusing on them, focus on the shape, texture, or the relational data instead of the brightness or face recognition. So these systems maintain performance, okay, where the human perception fail, because we think differently, we look at things differently as compared to the machines. All right, so then we have the augmented training data, which I have discussed with you. Advanced matching techniques. So what are the advanced matching techniques? Like uh, this course is not about image processing, just to give you an idea. So what are those techniques, which is called as metric learning, okay, which I'm not discussing, attention mechanisms. They help in what they help in identifying the relevant features. And those features are identified by minimizing the lighting effect, because if the lighting effect or is taken into consideration, then the recognition would not surpass human recognition. So what is the outcome? The outcome is that these methods allow for more reliable and consistent repeatedly matching than the human intuition. Humans surpass in certain areas, but this is the specific area where we have the lighting, where the machines surpass. And of course, this works when there are drastic changes in the illumination or the lighting conditions. Cross domain adaptation. So what does it means? This representations can be from different lighting domains, and the algorithms learn. Those reinforcement learners learn to recognize face, okay, seen under one type of lighting conditions, for example, like daylight versus dim lighting versus afternoon versus near the noon. However, that is not case for us, for humans, because we misidentify while the models adapt, okay, to those different lighting times. And what is the outcome? The outcome is better consistency. So temporal, what is meant by temporal consistency? For example, consider the case of videos where the we have different images at different times. or we can have a sequence of images, right? So that the effect of time is there. So these reinforcement learning algorithms, they track the facial features over time. Okay. And what is the outcome? They're able to maintain the identity of the person despite the lighting shifts, because with time the lighting shift takes place, and this helps filter out certain issues and certain artifacts, okay, which give these systems an edge over humans, because humans, they just like they rely on single moments, okay, and they are affected by other things. All right, so let's move on to the next concept. So how do okay, so move on to the next concept. So how do, for example, hidden Markov models, okay, or Gaussian mixture models compare with the deep learning techniques which are used today? This is interesting. Now this is a kind of a challenging, so to say, or a tricky question, that how do hidden Markov models and Gaussian mixture models compare with deep learning techniques? Now, people who are kind of like old folks, they hold to their old beliefs, and I'm not being sarcastic here. And they believe that the HMM and the GMM compare with deep learning techniques. Well, the deep learning techniques are like way ahead of these HMM and GMM architecture, which I will briefly explain to you here. And there's no comparison, as a matter of fact. So let's go one by one. So let's first talk of the model structure. And there is a nice diagram also, which will discuss towards the end. So this is the nice diagram I was referring to. This is basically, you have this hidden Markov models, and you have this Gaussian mixture models. Okay. So how does it works? So so these basically use a combination, right? And hidden Markov models are for temporal modeling, right? That we, I believe, discussed in some other course also. And then is the Gaussian mixture model, that is for probabilistic feature representation. So it's a combination of both of them. However, deep learning models like RNN or CNNs, they use layered neural networks in hundreds and thousands of layers. And by virtue of these layers, they are capable of learning complex hierarchical patterns end to end, right? And that offers more powerful and flexible model structures as compared to a combination of HMM and GMM. There is no comparison, as a matter of fact. Then is the feature representation. Sorry about that. Feature representation. Now, the HMM and GMM, they rely on handcrafted features or spectral coefficients, which is domain dependent, which means that it requires domain expertise. As opposed to them, deep learning techniques learn feature representations automatically from raw data. There's no human in the loop. So it's very fast. And that enables more nuanced and discriminative features identified that adapt better to complex data variations. Such features may not be visible to humans. So there's no comparison. Then is the data requirement. Now, it may seem that HMM and GMM, okay, they perform adequately. They perform adequately for limited label data due to their probabilistic foundation. And of course, with limited data, there is less richness, as a matter of fact. There is less diversity. As opposed to them, deep learning methods, they typically require large volumes of labeled data to train effectively. I've shown you a picture or a diagram also. So what is the plus side? It benefits from data richness, diversity, volume, and that results in better or improved generalization and better performance. which the HMM and GMM lack. So you should not be discouraged when people say that, well, what is special about this? This has been around for 50 years. That is not the case. That is ancient stuff. Accuracy levels, deep learning techniques generally overall typically achieve higher accuracy as compared to HMM and GMM, especially in noisy data or complex environments. Okay, why? Because of those hundreds and thousands of layers, they are able to model the non-linearities and the hierarchical patterns. That's the flexibility, which is not there in HMM and GMM, which lag in performance. Okay, when you have large and diverse data sets, they were not meant for that kind of a volume. Remember that when hidden Markov model was proposed, who would have, as a matter of fact, in the wildest imagination, guessed the volume of data which is being generated, which is being captured, which is so much diverse, right? Nobody could not even comprehend. And the processing power which will become available very cheap to process that data. So how can those models have can cater to such kind of challenges? And finally is the flexibility and the scalability. So these deep learning architectures are highly flexible. They're highly scalable. You just keep on adding the hardware, and they can adapt to various tasks. Okay, by modifying the layers or by using the training regimes. As opposed to them, HMM, GMM, I have limited scalability, limited flexibility, and their structures are dependent on the constraints, and they have a big problem adapting to new tasks or larger data sets. So they are good for a historical perspective, but they are not good for a practical application point of view. So this is the GMM HMM mixture model, and this is the data. These are the observations. It could be audio, color coded, and this part is used by the GMMs, and corresponding there is the state of the hidden Markov model, and it is moving between those states. And what is not known to us that what is causing that change, that's the hidden part. So why we need image networks? What, as a matter of fact, you must be wondering, so what is the image network? Because they have large, they have like 14 million images, right? And of course they are used for research, also for benchmarking, also for standardization, also for competitive environment, and so on. So the details you can read, okay, and at the end there's a nice diagram also. So what is the purpose of this image networks? For visual benchmarking. So what is visual benchmarking? Visual benchmarking, they provide a standardized large scale data set, okay, which is used as a benchmark, as a standard for doing evaluating and comparing what the performance of deep learning models, and in the domain, of course, of since images, so image recognition, and of course that helps in consistent progress tracking, and of course that allows fair assessment of different architectures, right? And of course that helps, right? So feature transferability. So the networks that have been trained on ImageNet, okay, they learn the hierarchical features, okay, which are there in the images. And of course when those features have been learned, they can be transferred to other computer vision tasks. What are the tasks? Such as object detection or segmentation or reducing the training time. And of course that improves the uh, when even if the task has is limited. And then is model generalization. So what is model generalization? So that helps to generalize better to unseen data. Okay, to unseen data. Basically, what has not been seen, that is classified based upon what has been seen. Why? Because the representation is robust, and how it is robust, because it captures wide variety of visual patterns and object categories. And what else? Deep architecture validation. So it is a critical platform, right? For validating, for checking deep network architectures when people introduce them, and that allows the researchers to test the innovations on challenging data set, on real world data set, and that can help identify, confirm if there is improvement on the as compared to the existing solutions. And of course, that accelerates the research. Why? Because there is a large label data set which is pre-trained, okay, and of course that helps in faster experimentation and reduces the time to gather massive data sets, right? So if we look at this picture here, I'm not going into any details of that picture set. This is a data set. So you can see that these are the training images in the red box, and then they are the test images. And of course, uh, the test images are from the same domain, right? You cannot compare flowers with elephants or dogs with aircraft carriers. So, but it's a large data set, and it helps a lot in different applications. So with this, we finish this topic.